Okay, so looking at this question from the 2021 AP Maths paper, we see that we have a quotient where the degree of the denominator is less than the degree of the numerator, i.e. that it's not so easy to partialize. We still have to change it back to the regular form of the degree of the numerator being less than the denominator. This question is worth the most marks out of the integration section at a sum total of 11 marks. So I'll try my best to explain it in a way that's concise yet clear. When we find problems of the form where the degree of the numerator is greater than that of the denominator, there are three strategies which we need to think of and use. The first one being polynomial division, where we essentially divide these two expressions by one another in the classic form where we put one of the expressions here and one there, and then come up with the dividend here. However, this method has proven to be very tedious, and I will not be going through that because this method of manipulating the expression to add or subtract a form of 0 is far more powerful. Before I get into that method, I will say that in general, when you find problems of this type, it will generally be that this will reduce to x plus a over the x minus 1 plus b over x plus 1 if we just factorize the denominator. It generally is of the type that if you have x cubed over x squared, then what will be left as this term with the x, and it would just be the x. And it's in general that if you had something like x to the 4 over x squared plus or minus whatever, plus minus whatever, that term in front would be like an x squared. So in general, you would just go ahead and divide these two if you're running out of time and you don't want to make sure of it. It's just a general rule of thumb. However, the right quote-unquote way of doing this would be to add or subtract a form of 0 from the expression, such that you can factorize it and cancel a term in the denominator with a term in the numerator, so that the overall new expression has the degree of the numerator less than the denominator. So if we just observe the numerator, we would need to insert an x squared minus 1 term into it somehow so that we can factorize it out. So if we look at the expression x cubed minus 3, we essentially want to get rid of this x cubed. We want to factorize it out by cancelling. So how are we going to do that? We're going to want to plus or minus some form of 0 from that expression so that we can generate that. So what we really want is, we want there to be a situation where it's like x into x squared minus 1, because we have the x cubed, so we need to essentially use logic to make sure that we are able to add or subtract a term whilst also using what we have. So we have the x cubed there, and we want to cancel with an x squared minus 1, so it would be easiest that we had a term like this. But we can't do this in maths. We can't just add and subtract things willy-nilly. We kind of have to make sure that everything is always balanced, as Thanos would love it. So in this case, what have we changed to the expression? Over here, in this part, we now have x cubed minus x minus 3. So how are we going to correct for that? The expression, the term rather, that we've added is this negative x. So we've got to correct for that x by adding it. Now, by plussing and minusing an x, we've reverted back to 0 by the term that we've added and subtracted, so we haven't changed the expression at all. In fact, if you look at this if you actually add and subtract that, you're just left with x cubed minus 3, which is what we had in the beginning. So now we know that we can rewrite this, just focusing again on the integrand, we can rewrite this as being x into x squared minus 1 plus x minus 3 all over x squared minus 1. Now, in a fraction of this type, we should be knowing from many years earlier that we can actually group these terms together, since we have one term in the denominator and multiple in the numerator. We can group these like that and essentially separate them. Now on the term highlighted in this orangish, reddish color, we can actually cancel that out. and that's now leaving us with just the x plus x minus 3 all over x minus 1, x plus 1. Okay, so this is now what we're integrating. This whole big thing here is what we're integrating. So we're going to take care of this x a bit later because this is extremely easy to integrate. So we're just going to focus on this portion right here. So with that comes the Heaviside's cover-up rule, which is essentially how you find the constants and how you partialize this in a pretty easy way. So in general, since we have a quadratic in the denominator with two non-repeated roots, we expect that we're going to partialize this into something of the form a over x minus 1 plus b over x plus 1, sorry. So the way that we're going to end up getting this is through the cover-up rule, as mentioned. So in order to get a, we cover up that x minus 1, and we replace it by the number which makes the term 0. So what would make this term in the denominator 0? It would be 1. So if we replace x with 1 in this case, we get 1 minus 3 over 1 plus 1, which is negative 2 over negative 2 over 2, which is negative 1, which means a is equal to negative 1. By a similar process, replacing x with negative 1 for getting b, we find that b is equal to positive 2. And that's it. Now we're left with the overall integrand being simply x plus 2 over x plus 1 minus 1 over x minus 1, which is a hell of a lot easier to integrate than that. So now just going term by term, we know that the integral of x is x squared over 2. We know that this, you can pull out the constant out front, 2, and we know that's ln absolute value of x plus 1. And then here, minus ln x minus 1 plus c, of course. Now, in theory, you could move the 2 there to the exponent, and you could move the negative up there as well, and you could probably even try combine these two. But for now, leaving it in this form is perfectly fine, and this would net you your whole 11 marks for this question. Now, I definitely think the biggest trick came along with not trying to use polynomial division, because polynomial division would have been very bad for this, and it would have taken you a long time. And using the cover-up rule to get the coefficients is the simplest method when you have a problem of this type, where it's simply non-repeated roots in the denominator and an easily factorizable expression. Hopefully this helped, and see you next time.